In this episode 3.8, we'll be talking about using multiple coprocessors in a cluster environment. Consider a cluster which has multiple machines called compute nodes, with one or several coprocessors per node connected into a common network. As we know from earlier episodes, we can use a parallel framework called MPI to scale an application across those compute nodes.
There are two fundamental approaches to using coprocessors in MPI applications in a cluster. The first one is based on the offload model. In this approach, we use MPI to scale across multiple compute nodes. We use the offload model to distribute work across multiple local coprocessors, and we use OpenMP to scale across the cores of CPUs and cores of coprocessors. The advantage of this model is that there are only as many MPI communication endpoints as there are nodes in the cluster. This means that MPI traffic may be lower than in alternative approaches, which we discuss later. The disadvantage is that if we want to use this model for applications that are already designed for CPU-based clusters, we'll have to modify the code and implement offload. Another approach to scale across multiple nodes with Xeon Phi coprocessors is based on the native programming model and use only MPI. MPI is used to scale across multiple compute nodes, across multiple coprocessors in each node, and to scale across the cores in each coprocessor. In this case, we put one MPI process on each core of a CPU and each core of a coprocessor. This naive pure MPI approach has the advantage that there is only one level of parallelism, process parallelism with MPI. Another advantage is that applications that can scale across a cluster may be run on Xeon Phi coprocessors without modification. However, there are disadvantages of this model. First of all, there are maybe up to 244 MPI communication endpoints on each coprocessor, which may overload the network. Another problem is that the memory overhead of up to 244 processors may be too high to fit in the coprocessor memory. There is a modification of the pure MPI approach illustrated in this diagram. This is a hybrid OpenMP and MPI model. Here we use MPI to scale across multiple compute nodes and across multiple coprocessors inside each node. However, we use OpenMP to scale across cores in each coprocessor and processor. We can even do some fine-tuning and use not one but 2 or 4 MPI processes on each CPU or Xeon Phi. The advantage of the hybrid OpenMP plus MPI approach is that we can use it to accelerate applications for CPU-based clusters that are already using MPI and OpenMP. And we do not have to implement offload in the code in this case. The disadvantage is that MPI communication has more endpoints than in the offload approach, and that peer-to-peer messaging between coprocessors must go through virtualized network, which may be less efficient than physical communication between hosts. Now let's talk about virtualized networking for peer-to-peer communication between Intel Xeon Phi coprocessors. If you are using MPI for communication, the details of the data movement at the hardware level are not visible to you. However, it is useful to know what goes on behind the scenes when MPI messages are sent, because it may be helpful to design more efficient communication in distributed calculations. First, let's focus on just one compute node with one or several Intel Xeon Phi coprocessors. As we know, coprocessors do not have Ethernet or InfiniBand ports. However, they can connect to the host's network ports thanks to virtual networking in MPSS. The diagram on the left shows the default network configuration in MPSS. The default configuration assigns IP addresses to coprocessors and allows them to exchange TCP/IP packets between local coprocessors and localhost. The TCP/IP packets to and from Xeon Phi coprocessors physically travel across the PCIe bus, but in the operating system it looks like communication goes on across virtual network interfaces called MIC0, MIC1, and so on. This TCP/IP network fabric is configured by default, and it is used, for instance, for SSH connections with the coprocessors, for network file sharing with NFS, and, if needed, by MPI. Programmers must know that as of the MPSS 3.4 and the first generation Xeon Phi coprocessors, this fabric has relatively low performance. Its bandwidth is capped at around 20 megabytes per second. However, as the diagram on the right illustrates, it is possible to improve communication between the local host and the local coprocessors by configuring InfiniBand software on the compute node. The software that needs to be installed is an Open Fabric Enterprise Distribution or OFAD that integrates with MPSS. This software can create a virtual InfiniBand network, and the local host and coprocessors can exchange InfiniBand verbs across a virtual network interface. This interface is referred to in documentation as ibscif, and its name in operating system is scif0. The virtual InfiniBand fabric complements the virtual TCP/IP interface, but the direct purpose of the InfiniBand fabric is MPI messages. The performance of messaging between the host and coprocessors is close to the maximum physical throughput of the PCIe bus, and communication between coprocessors is close to that. Now let's discuss communication between multiple compute nodes with Intel Xeon Phi coprocessors. Because coprocessors do not have network interconnects on board, they can communicate with coprocessors in other compute nodes only with the help of the operating system on the host. The diagram on the left shows a modified TCP/IP networking configuration with what is called an external networking bridge. This is a standard operation in Linux. We take the host's Ethernet interface and attach it to a virtual interface configured as a bridge, and then coprocessors attached to that bridge. What it does, it exposes the Xeon Phi coprocessors to the private network of the hosts. That means that a coprocessor in node A can send a TCP/IP packet to a coprocessor in node B. Physically, host A will deliver this packet to the network switch will deliver it to host B, and that host will deliver the packet to the local coprocessor. This bridge configuration is, again, useful mostly for administrative tasks. Even though it is possible to run MPI communication between coprocessors across an external TCP/IP bridge, this traffic will be limited in bandwidth at around 20 MB per second, even if the network is capable of greater bandwidth. Once again, in a cluster we can take advantage of InfiniBand to improve communication performance. Take a look at the diagram on the right-hand side. In this diagram we have a new element, a host channel adapter, or HCA. This is an InfiniBand network interface, which allows high bandwidth and low latency communication between hosts connected to it. With the help of OFET integrated with MPSS, the host's InfiniBand connection can be used to exchange MPI messages between Intel Xeon Phi coprocessors. The software functionality for this is called the Coprocessor Communication Link, or CCL. When CCL is at work, InfiniBand traffic from the coprocessor in host A travel across the PCIe bus directly into the HCA and from there into the InfiniBand network. If the destination is a coprocessor in node B, then that coprocessor will receive the message from the HCA and across the PCIe bus. This virtual InfiniBand has significantly greater performance than virtualized TCP/IP fabric with bridging. We discussed network configuration for peer-to-peer communication between Intel Xeon Phi coprocessors. Remember that this is important only for MPI applications in which processors run natively on coprocessors. For MPI applications based on the offload programming model, communication takes place only between hosts, and network configuration is done in the same way as for clusters without coprocessors. For more information about networking and for benchmarks, refer this Colfax research publication, xeonphi.com/papers/p2p.
Thank you for tuning in. In the next episode, we will continue talking about specifics of heterogeneous MPI programming for Intel Xeon Phi coprocessors, and we'll cover I/O functionality available on the coprocessors. I hope to see you in the next episode.